Ever feel overwhelmed by the sheer complexity of data? Let's face it, we live in a world that's brimming with data. Every click, every swipe, every interaction, it all generates data. And it's not just simple, straightforward data. It's complex, multifaceted, and often downright confusing. Dealing with this vast landscape of information can be daunting. We are confronted with a web of variables, a maze of correlations, a torrent of numbers that can seem impossible to make sense of. The challenge lies not just in collecting the data, but in extracting meaningful insights from it. How can we sift through this data deluge? How can we unravel its intricacies to reveal the patterns and trends hidden within? How can we transform this complexity into clarity? The solution doesn't lie in more data, nor in more sophisticated data collection tools. Instead, it lies in a mathematical technique that's as elegant as it is effective. The solution to simplifying data lies in a technique known as principal component analysis. So, what exactly is this principal component analysis? Let's dive in. Imagine you're at a bustling farmer's market. There are fruits, vegetables, spices, all sorts of goods. Each vendor has a myriad of items, each with its own price, weight, color, and so forth. Now imagine trying to make sense of all this information. It's overwhelming, isn't it? Enter Principal Component Analysis, or PCA for short. Like a seasoned market shopper, PCA helps us navigate through this sea of information, simplifying the complexity we're faced with. But how does it do this? Well, PCA is a method that brings out strong patterns in a dataset. It does this by creating new artificial variables called principal components. These components are a linear combination of the original variables, but here's the catch. They're designed in such a way that the first component captures as much of the variance in the data as possible. Subsequent components, each orthogonal to the last, capture as much of the remaining variance as they can. In simpler terms, PCA is like creating a new map of our farmer's market, but instead of mapping each individual item, it maps broader categories, like fruits, vegetables, and spices. These categories, or principal components, capture the most essential information, allowing us to understand the market without getting lost in the details. So when we're faced with a large, complex dataset, we can use PCA to distill the data down to its most essential parts. This makes it easier to interpret and understand the underlying patterns and relationships. It's like having a compass guiding us through the labyrinth of data. But it's important to remember that PCA is not a magic bullet. It's a tool, and like any tool, it needs to be used appropriately and with understanding. It can simplify data, but it can also oversimplify if not applied carefully. In essence, PCA is a statistical procedure that uses an orthogonal transformation to convert a set of observations into a set of linearly uncorrelated variables. And that, my friends, is the heart of principal component analysis. Now, how does principal component analysis work, you might ask? Well, it's time to delve into the heart of the matter and break down this complex process into manageable steps. First and foremost, we have to standardize our data. This is a crucial step because principal component analysis is sensitive to the variances of the initial variables. So, if one variable has a broad range of values, it might dominate over the others. To avoid this, we scale our data so that each variable has a mean of 0 and a standard deviation of 1. This way, all variables are on an equal footing and none overshadows the others. Once the data has been standardized, we move on to compute the covariance matrix. The covariance matrix is essentially a table that shows how much the variables change together. If two variables increase together, they have a positive covariance. If one increases while the other decreases, they have a negative covariance. It's a snapshot of how our variables interact with each other. The third step involves the computation of eigenvalues and eigenvectors. These mathematical concepts might sound intimidating, but they are quite simple to grasp. The eigenvalues tell us the amount of variance in the data that is explained by each principal component, while the eigenvectors give us the direction of these components in the data space. In layman's terms, they provide us with the information about the length and direction of the principal components. The final step in our process is the sorting of eigenvalues. Here we rank the eigenvalues from highest to lowest, and by doing so, we rank the corresponding principal components. The component with the highest eigenvalue becomes our first principal component. This is the direction in our data space along which the observations vary the most. The second principal component is orthogonal to the first and accounts for the second most variance, and so on. By sorting the eigenvalues, we essentially decide the order of importance of our principal components. This allows us to reduce dimensionality while retaining the most valuable parts of our data. We can then choose to keep as many components as we need based on the cumulative explained variance. So there you have it. From standardizing our data to computing the covariance matrix, to finding eigenvalues and eigenvectors, and finally sorting the eigenvalues, these are the steps that encapsulate the process of principal component analysis. It's a journey of understanding the intricate relationships within our data and then simplifying them into a digestible format. By following these steps, one can successfully perform a principal component analysis. And remember, the beauty of principal component analysis lies in its ability to transform complexity into simplicity. It's not just about reducing dimensionality, it's about making your data tell a story in a more streamlined and insightful way. Let's take a moment to recap the key points of principal component analysis. Principal component analysis, often abbreviated as PCA, is a statistical procedure that uses an orthogonal transformation. This transformation converts a set of observations of possibly correlated variables into a new set of values known as principal components. These principal components are linearly uncorrelated, making them easier to manage and analyze. Now, the purpose of PCA is twofold. Firstly, it is used to simplify complex data sets. By reducing the dimensionality of the data while retaining most of the original variance, PCA helps us to visualize and understand the data better. Secondly, PCA is used to eliminate redundant information. By focusing only on the principal components, we can discard the rest of the data that provides little to no unique information. The process of PCA begins with standardizing the data. This is essential as it ensures that each variable contributes equally to the principal components. Following this, we compute the covariance matrix, which helps us understand how different variables change together. The next step involves finding the eigenvalues and eigenvectors of this covariance matrix. These eigenvalues and eigenvectors form the backbone of PCA, as they help us find the principal components. The eigenvector with the highest corresponding eigenvalue is considered the first principal component, as it explains the most variance in the data. Subsequent principal components are chosen in the same way, with the condition that they must be orthogonal to the preceding components. This orthogonality ensures that each principal component represents a unique variance in the data. The number of principal components is usually less than or equal to the number of original variables, which helps in simplifying the data. Now, the importance of PCA in simplifying complex data sets cannot be overstated. In data science, we often deal with high-dimensional data. Trying to visualize or analyze this data in its raw form can be like trying to navigate a maze in the dark. But with PCA, we can shed light on the structure of the data, making it much easier to understand and interpret. However, it's crucial to remember that PCA is not a magic solution. It does not make irrelevant data relevant, nor does it create information where there is none. It simply highlights the most important features of the data, allowing us to focus our analyses on these features. Therefore, PCA requires careful interpretation and understanding. It's a powerful tool, but like all tools, it must be used wisely. In conclusion, principal component analysis is a key statistical technique that helps us simplify and interpret complex data sets. It is a process of transformation, reduction, and illumination, turning a dense forest of data into a manageable garden of insights. Remember, PCA is a powerful tool for data analysis, but it requires careful interpretation and understanding. Why does principal component analysis matter in data science? Well, let's dive into it. Principal component analysis, or PCA, is an unsung hero in the realm of data science. It's like a secret weapon, a tool in the data scientist's arsenal that helps to unravel complex data sets and serve up insights that are easier to digest. Imagine you're dealing with a data set that has hundreds or even thousands of variables. Trying to navigate through that sea of information can be daunting, to say the least. This is where PCA steps in. By reducing the dimensionality of the data, it distills this ocean of variables down to its most essential components. This not only makes the data more manageable, but also helps to eliminate noise and any redundant information. PCA is also a champion when it comes to data visualization. Human beings are visual creatures. We understand and interpret visual information better than any other form of data. But visualizing high-dimensional data can be quite a challenge. PCA simplifies this process by transforming the high-dimensional data into a 2- or 3-dimensional data set. This allows us to create plots and graphs that provide clear visual representations of the data. Beyond simplification and visualization, PCA plays a crucial role in predictive modeling. By reducing the number of variables, PCA helps to create models that are less complex, more interpretable and faster to run. This not only makes the modeling process more efficient, but also helps to improve the accuracy of the predictions. That's not all. PCA is also instrumental in various other data analytics tasks, such as clustering, anomaly detection, and feature extraction, to name a few. By highlighting the most important information in the data, PCA helps to reveal patterns and trends that might otherwise remain hidden. In conclusion, principal component analysis is a critical technique in data science that aids in the simplification and interpretation of complex data sets. It's like having a compass in the vast sea of data, guiding us towards the insights that truly matter.